In this project, we will investigate the fluid flow problem and heat transfer inside a pipe in 3 dimensions. Now, as you know, the first step is to click on a fluid flow block and then drag it into the blank space inside Workbench software and then double click on Geometry section. Now, in order to design the cross section of our geometry, we click on XY plane and then click on the Sketch button. After clicking on the sketching button, we click on circle and then draw a circle in the middle of our coordinate system. Now, after drawing the circle, in order to give dimensions to the circle, we click on dimensions and then select on semi-automatic. Now, under the dimensions, we enter the value of diameter of our circle to be equal to 0.05 meters. Now, after drawing the circle, which would be the cross section of our pipe, we click on extrude button and then extrude this circle with a length of 2 meters. The next step is to create a rectangular cross section in the middle section of our pipe. Now, this rectangular cross section will be used in meshing section to generate a structured mesh easily. To create such geometry, we click on XY plane and then click on the sketching button. To create such a structure, we click on sketch number 2 and then click on the sketching button and then select rectangle and then draw a rectangle in the middle section of our coordinate system. After drawing the rectangle, we click on Dimensions and select Semi-Automatic, and we enter the dimensions of our rectangle so that it will be placed in the middle of our coordinate system. In the following slides, you can see the values of dimensions for the rectangular that should be placed in the middle section of our coordinate system. Now, after drawing the rectangle, we click on Extrude button and then select the sketch number 2 as we want to extrude this sketch. After that, in front of the geometry, we click on Apply button, and then in front of the operation, we change it from Add Material to Add Frozen so that this rectangular extruded body will have the same material just like the pipe. And then we click on Generate button. Now, in order to separate these two extruded bodies from each other, we click on Create button and then select Boolean. On the low left side of the software window, we change the operation from unit to subtract. And then in front of the target body, we select the pipe, and in front of the tool bodies, we select the rectangular extruded body. Now, below the tool body section, you can see the software is asking you a question whether you want to keep the subtracted body or not. By asking you, do you want to preserve the tool bodies? Since we want to keep this body, we select yes in front of Preserve Tool Bodies section. Now, in order to create a structured mesh, we need to divide our body into different sections. To do that, we click on Plane, and then on the low left side of the software window in front of the base plane section, we select YZ plane and then click on Apply. It should be only pointed out that the coordinate system you can see in the middle section of the Design Builder software has different direction from the coordinate system that you can see on the right corner. However, the color of the direction of each coordinate system still is the same. For example, the red color still represents the X direction, the blue color represents the Z direction, and the green color represents the Y direction. Now, after selecting the base plane, which would be the YZ plane, under the transform section we select rotate about Y. It should only be pointed out that the coordinate system you should use in this part is the coordinate system you can see in the middle section of your geometry. Then in front of the FD1 value, we enter the value of 45 degrees and then click on Generate button. Now we need to create another plane following the same exact step, but with the difference that in front of the FD1 value, we should enter the value of minus 45 degrees. Now after creating these two planes, we need to use the slice command in order to separate our geometry into two different sections. After clicking on the slice button, we should select our first plane, and then in front of the base plane we click on the apply button. After that, in front of the slice target, we should change this option from all bodies to selected bodies. After changing the slice target from all bodies to selected bodies, below this, in front of the bodies, we select the outer geometry, which would be the pipe geometry. After using this command, you can see that the outer geometry of the pipe is divided into two sections. Now we need to perform the slice command again in order to divide our pipe geometry into four sections. Now we follow the same previous steps, but with the difference that this time we select the second plane and then click on apply. After selecting the base plane in front of the bodies, we select the two side bodies related to the pipe geometry. Now, since we want to solve our problem in a symmetric form, we need to use slice command one more time in order to divide our body into two separate symmetric sections. After clicking on the slice button, we select YZ plane, and then in front of the base plane section we click on apply. But this time we won't change the slice targets, and we set it to be all bodies. If you follow the same steps, you should now have 8 different bodies in your geometry. Now, since we wanted to solve our problem in a symmetric form, we should suppress half of these bodies. To do that, we click on a button which let us select the bodies. And then we select the bodies that are placed on the right side of our geometry. After selecting these four bodies, we right click on them and then click on suppress. In this way, those bodies will be omitted from the geometry you can see in the software. After that, on the tree outline section, we select and click on the bodies that are left and then right click and select form a new part so that this separated body would count as a whole part in order to avoid any problems in meshing section. After creating one part out of these separated bodies, we click on this part and then on the low left side of the design software in front of the fluid or solid section, we select fluid since the fluid flow will pass through this pipe. After that, you can save your project and then close the design software. After designing the geometry, the next step is to generate mesh for it. To do that, we double click on the mesh button. As you all probably can remember, in order to give sizing to each of these edges on the geometry, we have to right click on mesh and then go over insert and select sizing. For the simplicity in selecting different edges, we first click on edge button and then click on the edges that we want to give sizing. For example, for the first sizing, we select the edges that are placed radially and then set 15 mesh cells over each of these edges. We also change the behavior type from soft to hard, and in order to have smaller mesh cells near the outer wall of our pipe, we use bias option. In front of the bias type, we select the first option, and then in front of the bias factor, we enter the value of 3. As was explained previously, we wanted to have smaller mesh cells near the outer wall of our pipe, therefore we need to change the direction of mesh cells in two edges. While holding down the control key, we select these two edges and then in front of the reverse bias section, we click on apply button. Now for the next sizing, we would select the edges that are placed horizontally and the edges that are placed on the upper and the lower part of the pipe. After selecting these four edges in front of the geometry, we click on apply and then we set 10 mesh cells over these edges and change the behavior type from soft to hard. We also do the same step for the edges that are left. But this time we set 20 mesh cells over these edges, since these edges are 2 times bigger than their previous edges. Now at this point we are going to use the sweep method in order to extend the mesh cells that we had defined over one face of our geometry in its depth. To do that, we right click on mesh and then go over insert and then select method. Now we need to select all different parts in our geometry. To do that, we right click on a blank space and then go over select all button. After that, in front of the geometry, we click on apply, and then in front of the method, we change it to sweep method. After selecting the sweep method, you will see that a new part will be shown to you. In front of the SRC TRG selection, we change it from automatic to manual source. And then in front of the source, we have to select the face that we had previously defined mesh cells over it. Now, since we wanted to generate quadrilateral mesh inside our geometry too, in front of the free face mesh type, we select all quad, and then in front of the sweep number division, we enter the value of 500. Now, in order to better capture the starting point of the fluid boundary layer, we need to have smaller mesh cells at the inlet boundary. To have such mesh cells in front of the sweep bias type, we select the first option and we set the bias factor to 3 again. Now it's time to set names for the different boundaries of our geometry. After selecting these 4 edges, we right click on it and then select create name selection, and we gave the name of inlet boundary. Now the 3 faces that are placed in the middle section of our geometry would be our symmetry boundary. And we define the outer wall boundary, as you can see in the following slides. Now for the outlet boundary, we rotate the geometry to its other side and we select the faces that you can see here and name them as outlet boundary. Now the final step is to define the flow volume boundary. To do that, we click on body selection button and then right click on a blank space in the geometry section and then go over select all. After doing that, we right click on it and then click on create name selection and we name it as flow boundary. Now it's time to generate the mesh. To do that, we right click on mesh button and then select generate mesh button. Now that the mesh is generated, we have to check that the mesh cell sizes near the inlet boundary is correct. Now if you compare the mesh cell sizes at the inlet boundary and near the outlet boundary, you will understand that the direction of our mesh cells in the sweep method is correct. Now if the mesh cell sizes was wrong in your project, you can simply right click on sweep method and then click on edit and then change the bias type direction. Now after that the mesh was generated correctly, we close the ANSYS meshing software and then double click on setup button to launch the Fluent software. In the appeared window under the options, we enable the double precision option, and under the parallel in front of the solver processes, you can enter the number of CPU cores you want to use in order to solve your problem. By clicking on check button, you will see that under the console tab, the Fluent software will start to check your mesh for any errors. Also by clicking on report quality, again in the console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. Now there are several assumptions taken into account for this project. First, the type of our solver is defined to be pressure based since we are dealing with incompressible flows, and for the time study we have selected the a steady time study since we didn't want our results to be a function of time. Since we want to solve heat transfer inside our computational domain, we double click on energy button and then enable the energy equation. After double clicking on the viscose button, a new window will appear. In the appeared window, you will see that we have chosen two equations, standard K epsilon, to solve for our fluid flow. The standard K epsilon model is one of the most renowned model for solving the turbulent fluid flows, and actually two equation K epsilon model allows the determination of both a turbulent length scale and time scale by solving two separate transport equations. Now, the standard K epsilon model is normally used for internal flow, just like the present project where we have fluid flow passing inside the pipe. This model uses a logarithmic function to estimate the velocity profile shape in the boundary layer. And before explaining the near wall treatment, we should introduce a parameter called y plus, which is equal to density multiplied by u star multiplied by t over mu. Now the u star is the velocity magnitude of the fluid flow perpendicular to the surface, and t is the thickness of the mesh cell. For example, for standard wall functions, y plus should have a value between 300 and 30, or for enhanced wall treatment, this value should have value lower than 5. Mainly, these near wall treatment models are used to better calculate the velocity shape profile in the boundary layer. Now if you expand the fluid under the materials, you will see that only air material is defined in the software, and that we need to define water liquid material since we want this fluid to flow inside our pipe. Now in order to add a new material, all you have to do is to right click on fluid and then select new. In the appeared window, you have to click on Fluent Database, and then in the newly appeared window, from the list of available materials in the Fluent software, you have to select the water liquid. Now in order to make the calculations for Reynolds number much easier, we change the value of density to 1000 and we change the value of viscosity to 0.001. Now that we have added the water liquid material in the software, we have to introduce this material inside our computational domain. To do that, we expand the cell zone conditions and then double click on flow zone. In the appeared window in front of the material name, we should change the material name from air to water liquid that we had previously defined in the material section. Now if you click on the inlet boundary, you can see that the type of this boundary is defined to be velocity inlet. By clicking on edit button, a new window will appear in which you can change the settings for this boundary. In the appeared window in front of the velocity magnitude, we enter the value of 0.4 meters per second so that it will represent the value of Reynolds number equal to 20,000. Under the turbulence section in front of the specification method, we change this option from intensity and viscosity ratio to intensity and hydraulic diameter. And then in front of the turbulent intensity, we enter the value of 1% so that we would make our fluid flow entering our computational domain less turbulent and therefore reducing the computational time. And in front of the hydraulic diameter, we enter the value of 0.05 as the diameter of our pipe. And under the thermal tab, we set the temperature of our fluid flow to 25 degrees centigrade or 298.15 Kelvin. After clicking on the outlet boundary, the type of this boundary is defined as pressure outlet. By clicking on Edit button in the appeared window under the Momentum tab in front of the gauge pressure, you can see we have entered the value of 0, meaning that our fluid flow will exit our computational domain to the atmosphere. Also under the turbulence section, we entered the same values that we entered for the inlet boundary. Now in the settings window for the outer wall boundary, under the Momentum tab, we can see stationary wall motion along with no slip shear condition are defined for this wall. Now in this project, we want to apply a 5000 watt per meter squared heat flux over the outer wall boundary. To do that, we click on Thermal tab and then under the thermal condition, we select heat flux. And in front of the heat flux, we enter the value of 5000. After double clicking on the method in the appeared part, you can see we have again used the simple scheme for our pressure velocity coupling. It should only be pointed out that under the spatial discretization, in order to increase our accuracy in solving the turbulence equation, we have changed the turbulent kinetic energy and turbulent dissipation rate scheme from first order of wind to second order of wind. In the control section, we don't need to change any value, and we let it be. Now under the monitor section, if you double click on residuals button in the appeared window, we'll lessen the values of our residuals for one order in order to make our simulation more robust. In the initialization section, we select the standard format, and under the compute from, we select the inlet boundary, and then we click on initialize button. After the initialization step, we double click on run calculations button, and under the number of iteration, we enter the value of 500, and then we click on calculate button, and the software will start the simulation process. Now as our first step, we are going to extract the graphical resulting contour. To do that, we expand the graphics section and then right click on contours and then select new. In the appeared window under the contours of section, we can select our desired variable. For example, in this stage we are going to extract velocity contours. So we select the velocity variable, and then under the surfaces section we select the symmetry boundary in order to see the velocity in the middle section of the pipe. And then we click on Save or Display button. Now if we zoom a little bit over this velocity contour near the outlet boundary, we can guess that our fluid flow has reached fully developed state. But in order to make sure that whether our fluid has reached the fully developed state or not, we can simply create a line in the middle section of the symmetry plane and see the changes of velocity over that line. To create such line, we right click on surfaces and then go over new and then select line or rake. And then in the appeared window, we enter the values of first and ending point, just as you can see in the following slides. Now that we created this line, it's time to create a plot where we can see the changes of velocity along this line. To do that, we expand the plot section and then right click over XY plot and then select new. In the appeared window under the plot direction, we change the value of x to 0 and we set the value of z to 1 since our line is along the z-axis. And under the y-axis function, we select the velocity, and then under the surfaces, we select our created plane and then click on Save or Plot button. Now, as you can see in this plotted diagram, the value of the velocity along this line has almost reached a constant value. However, it seems that we needed a little bit longer pipe than we have in this project in order for the fluid flow to reach fully develop the state completely. It should only be pointed out that the position with the value of 2 represents the inlet boundary, and the position with the value of 0 represents the outlet boundary. Now, as you all probably can remember, in order to extract the correct value of the Nusselt number, we should change the reference values. Now, in the reference values, we need to change the reference values for the length and temperature. Now, in the Nusselt number formula, the reference length scale is the diameter of the pipe. So in front of the length section, we enter the diameter of the pipe, which is equal to 0.05 meters. After entering the right value for the length, it's time to calculate the bulk temperature, and then set the value of the bulk temperature in front of the reference values for the temperature. To calculate the bulk temperature, we expand the report section and then double click on Volume Integrals button. In the appeared window, under the report type, we select volume average, and under the field variable, we select the temperature, and under cell zone, we select the flow zone, and then we click on compute button. After that, we copy the shown value and replace it in front of the temperature in the reference values section. Now, after this stage, we can correctly calculate the value of the Nusselt number. To calculate the average Nusselt number over the wall of this pipe, under the report section, we double click on surface integrals. In the appeared window, under the report type, we select facet average, and under the field variable, we select wall fluxed, and below it, we select surface Nusselt number. And then under the boundaries, we can select the outer wall boundary and then click on compute button, and the software will calculate the average Nusselt number for the outer wall boundary for us. Now, as you all probably know, and as was explained in previous slide, this value is for the average Nusselt number. Now, we can calculate the local Nusselt number using different ways. For example, we can create along the outer wall boundary and then plot the changes of local Nusselt number along this line. To do that, we right click on surfaces and then go over new and then select line or rake. In the appeared window, we enter the values of the first and ending points so that our line will be created on the middle section of the outer wall boundary. Also, in order to view your created line, you can simply double click on mesh under the graphics section and then click on line number 5 and then click on save or display button. Now that our line is created, in order to plot the changes of local Nusselt number along this line, we can simply right click on XY plot and then select new. Now in the appeared window, just like the diagram we plotted for the velocity changes along the line in the middle section of our symmetry plane, we change the values of x and z under the plot direction, and then under the y-axis function we select wall fluxes, and beneath it we select surface Nusselt number, and then under the surfaces we click on line number 5 and then click on save or plot button. You can also calculate the Nusselt number manually and using its formula. For example, in this stage we are going to show you how to create an arbitrary line over the outer wall surface and then calculate the value of surface heat transfer coefficient using the bulk temperature and the surface temperature. And then using the value of surface heat transfer coefficient, we can calculate the value of Nusselt number. To create such arbitrary line, we right click on surfaces and then go over new and then select isosurface button. In the appeared window under the surface of constant we select mesh and underneath it we select z coordinate. After that we click on compute button so that the software will calculate the geometry extents in z direction. Now that we know the minimum and maximum value for the geometry extents in z direction, under the ISO values, we can, for example, enter the value of 0.1 meter so that our surface would be placed near the outlet boundary. We also change the surface name in order to avoid any problems in next steps, and then click on Create button. Now, this is the surface that we have created in previous slides. In order to change this face into a line, we again need to create another isosurface. In the appeared window, we follow the same steps that we use in order to create the previous face, but this time with the difference that under the surface section, we select the outer wall boundary in order to make the software understand that we want the intersection of this face with the outer wall boundary. Now in this slide you can see that the intersection line that we needed is created and shown here. Now in order to calculate the value of surface heat transfer coefficient, we need to have two values of bulk temperature and wall surface temperature. To calculate these values, we double click on surface integrals button. Now in order to calculate the value of the temperature over the created line, as you can see in this slide, which is placed on the geometry, under the report type we select vertex average, and then under the field variable we select temperature, and under the surfaces we select the Z coordinate number 7, which represents the created line, and then click on compute button. Now, as was mentioned earlier, we need to calculate the bulk temperature. To do that, we change the report type from vertex average to facet average, and then under the surfaces, we select the surface that we had previously used to create the line that you can see in this window, and then click on compute button. Now that we calculated the values for wall temperature and bulk temperature, we can easily put those values in the formula for the surface heat transfer coefficient and calculate its value. After that, we can easily put the value of the surface heat transfer coefficient in the Nusselt number formula and calculate the Nusselt number manually. To benefit from Mr. CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.